This is the continuation of thermodynamics module. We covered the basic concepts, zeroth law, and thermometry in the last video. Now we will move to the rest of the sections. Section 3 is the first law of thermodynamics. Before we can fully understand the first law, we need to look at some important concepts. Joule's experiment. James P. Joule carried out his famous experiment where he placed known amounts of water, oil, and mercury in an insulated container and agitated the fluid with a rotating stirrer. The amount of work done on the fluid by the stirrer were accurately measured, and the temperature changes of the liquid was carefully noted. Now he found for each fluid that a fixed amount of work was required per unit mass for every degree of temperature rise caused by the stirring action, and that the original temperature of the fluid could be restored by transfer of heat through simple contact with a cooler object. From this experiment, we can conclude that there is a relationship between heat and work, or in other words, heat is a form of energy. Through Joule's experiment, we need to know what happens to energy between the time it is added to water as work and the time it is extracted to heat. Logic suggests that this energy is contained in the water in another form, which is called internal energy. Internal energy refers to energy of molecules of a substance which are in constant motion and possess kinetic energy. The addition of heat to substances increases this molecular activity and thus causes an increase in its internal energy. Work done on the substance can have the same effect, as it was shown by Joule. Internal energy cannot be directly measured as there are no internal energy meters. As a result, absolute values of internal energy are unknown. But this is not a disadvantage for us because in thermodynamic analysis, only changes in the internal energy are required. Now, enthalpy is a thermodynamic property that represents the total heat content of a system, and it is especially useful in analyzing energy changes in processes occurring at constant pressure, such as chemical reactions and phase changes. Enthalpy can be written as H is equal to U plus PV, where H is the enthalpy, U is equal to internal energy of the system, P is the pressure, and V is the volume. In practical thermodynamic processes like heating, cooling, or chemical reactions, systems often operate at constant pressure. Under such conditions, the change in enthalpy equals to the heat added to or removed from the system. Now coming to the first law of thermodynamics, it states that energy is neither created nor destroyed, and thus the total energy of the universe is constant. However, energy can certainly be transferred from one form to another. This is because when you add heat, internal energy increases or the system is doing work. And when the system does some work, it uses up internal energy or heat. The first law is important because it forms the foundation of all energy analysis in engineering, physics, and chemistry, and it helps predict system behavior. Because understanding how heat and work affect a system allows you to optimize performance, minimize energy losses, and ensure safety and reliability. During a thermodynamic cycle, the cyclic integral of heat added is equal to the integral of work done. So, we can write the first law mathematically as a closed integral of dq is equal to closed integral of dw. The equation du is equal to dq minus dw is a corollary to the first law of thermodynamics. It shows that there exists a property, that is internal energy of the system, such that a change in its value is equal to difference in heat entering and work leaving the system. So what is a corollary? A corollary is a situation, a statement, or a fact that is the natural and direct result of another one. There are three corollaries for the first law. Corollary 1 says there exists property of closed system such that the change in value of this property during the process is given by the difference between heat supplied and work done, where E is the property of the system and is called the total energy that includes internal energy, kinetic energy, potential energy, electrical energy, magnetic energy, chemical energy, all of them. Okay. Corollary 2 says for an isolated system, heat and work both interactions are absent. dq is 0 and dw is also 0 and energy is constant. Because energy can neither be created nor be destroyed, but it can be converted from one form to another. Corollary 3 is the perpetual motion machine of first kind. It is a hypothetical machine that produces work continuously without any energy input, essentially creating energy from nothing. It violates the first law of thermodynamics, which states that energy can not be created or destroyed. Now, according to first law, change in internal energy is the difference between heat supplied and work done. So, if a machine outputs work without receiving any heat or internal energy change, it is creating energy which breaks the law of energy conservation. Imagine a motor that powers itself and also drives a generator to power other devices without needing fuel or external electricity. This would be a PMM1 and it is physically impossible. Despite many claims over centuries, no PMM1 has ever worked because energy inputs are always needed, friction and losses always exist, and you can't get more energy out than you put inside the system. Now, coming back to the thermodynamic processes that we discussed in the last video, in thermodynamics there are two types of processes: flow processes and non-flow processes. The flow processes in open system permits the transfer of mass to and from the system. Such process is called flow process, and the mass enters the systems and leaves after exchanging energy. For example, IC engines and boilers. For non-flow processes, the process occurs in a closed system where there is no transfer of mass across the boundary, and in such a process, the energy in the form of heat and work cross the boundary of the system. This is the complete classification of thermodynamic processes. First law applied to a flow process. Now, virtually all the practical systems involve flow of mass across the boundary, separating the system and surroundings. Whether it be a steam turbine or a gas turbine or a compressor or an automobile engine, there exists flow of gases or gas mixtures into and out of the system. So, we must know how the first law of thermodynamics can be applied to an open system. The fluid entering the system will have its own internal kinetic and potential energies. In many practical problems, the rate at which the fluid flows through a machine or piece of apparatus is constant. This type of flow is called a steady flow. There are some assumptions that are made in system analysis during steady flow. First, The mass flow through the system remains constant. Fluid is uniform. The only interaction between system and surroundings are work and heat. The state of fluid at any point remains constant with time. And in the analysis, only potential, kinetic and flow energies are considered. This is a schematic flow process for an open system. A wide interchange of energy may take place within an open system. Let the system be an automatic engine with inlet manifold at the first state point and exhaust pipe at the second point. There would be an interchange of chemical energy in the fuel, kinetic energy of moving particles, internal energy of gas and heat transferred, and shaft work within the system. This is obvious that there is no variation of flow of mass or energy with time across the boundaries of the system. The steady flow will prevail. The conditions may pass through cyclic or non-cyclic changes within the system. As a result, the mass entering the system equals to the mass leaving. Also, energy entering the system equals to the energy leaving. So the steady flow equation can be expressed as where Q is equal to heat supplied per kg of fluid, W is equal to work done per kg of fluid, C is the velocity, Z is the height above datum, P is pressure, U is internal energy per kg, and PV is equal to energy required for 1 kg of fluid, and H is the enthalpy. This equation is applicable to any medium in any steady flow, and it is applicable not only to rotary machines such as centrifugal fans, pumps and compressors, but also to reciprocating machines such as steam engines. Now here are some engineering applications of steady flow energy equations. In a water turbine, water is supplied from a height and the potential energy of water is converted into kinetic energy where it enters into the turbine, and part of it is converted into useful work which is used to generate electricity. Here you can see how we have derived the steady flow equation for the water turbine. Though this is outside the scope of our course, but I have still added it to the PPT so you can make notes out of it in case it comes as a question in any of your exams. In steam or gas turbine, the gas is passed through the turbine and part of its energy is converted into work in the turbine, and this output of the turbine runs a generator to produce electricity. Here the sign of Q is negative because heat is rejected, and the sign of W is positive because work is done by the system. Next is reciprocating compressor. The reciprocating compressor draws in air from the atmosphere and supplies at a considerable high pressure in small quantities. Okay. It can be considered as a steady flow system provided the control volume includes the receiver, which reduces the fluctuations of flow considerably. Change in PE is equal to 0 and changes kinetic energy also equal to 0. Now in case of a boiler, the boiler transfers heat to the incoming water and generates steam. So work will be 0 since neither any work is developed or absorbed, right? In case of a nozzle, as the enthalpy of fluid decreases and pressure drops, simultaneously the flow of fluid is accelerated. This is normally used to convert one part of energy of the steam into kinetic energy supplied to the turbine. Now let's look at some MCQs based on the first law. Question 1. The first law of thermodynamics is based on the principle of A. Conservation of momentum, B. Conservation of energy, increase of entropy, or conservation of mass. Correct answer is B. Conservation of energy, because it states that energy can neither be created nor be destroyed. Right. Question 2. What did Joule's experiment prove? A. Heat is not a form of energy. B. Mechanical energy and heat are not equivalent. C. Heat and work are interchangeable forms of energy. And D. PMM1 is possible. Joule showed that mechanical work done in stirring water increased its temperature, confirming the equivalence of work and heat. So the answer is C. Question 3. A perpetual motion machine of the first kind, or PMM1, violates A. zeroth law, B. first law, C. second law, D. third law. The answer is B. In a thermodynamic process, the first law is expressed as, answer is C, du is equal to delta Q minus delta W, because it's the differential form of the first law of closed system, where du is the change of internal energy and delta Q is heat added and delta W is work done by the system. Question 5. The steady flow energy equation applies to A. closed systems, B. static systems, C. open systems with steady flow, and D. isolated system. Now, steady flow energy equation is used for devices like turbines, nozzles, compressors, where mass enters and leaves under steady conditions. So, it is open system with steady flow. Question 6. Which of the following is not a part of steady flow energy equation? Okay. Enthalpy, kinetic energy, potential energy, or entropy? Answer is D. Entropy. Question 7. In a nozzle, applying steady flow energy equation and assuming no heat and work interaction, which energy component increases? Enthalpy, kinetic energy, potential energy, and internal energy. So now nozzle converts thermal energy into kinetic energy to increase velocity, right? So the correct answer will be kinetic energy. Question 8. Which of these processes do not violate the first law of thermodynamics? A. Machine producing work without input. B. System creating energy. C. Energy where input energy equals output plus losses. And D. Refrigerator with zero power input extracting heat. Answer is C. Energy where input energy equals output or losses, because this is the only one that obeys energy conservation, and other choices imply energy creation or imbalance. So those are not possible. These are some of the interview questions that you need to practice. Now we will move to the limitations of the first law of thermodynamics. The first law tells us how much energy is involved, but it does not tell us in which direction a process will naturally occur. For example, it allows heat to flow from a cold body to hot body, which never happens naturally. Next, first law cannot distinguish between work and heat quality. So it treats 1 kg of work and 1 kg of heat as equivalent, but in actual practice, work is more useful. That is, it is a high grade energy, while heat is a low grade energy, especially at lower temperatures. First law does not predict efficiency limits. It allows for the idea of a 100% efficient heat engine, that is converting all the heat into work, which is not possible in real life. Then the first law does not rule out any physical impracticalities. For example, while it helps us detect violations of energy conservation, it cannot explain why some theoretically allowed processes do not actually occur. Like the perpetual motion machine of the first kind, running forever without energy input. It doesn't address entropy, disorder, or irreversible processes, all of which are crucial in real-world thermodynamics. Hence, there are certain processes which are not possible to occur even though these processes do not violate the first law of thermodynamics. Let us understand this with two examples. Let's suppose a cup of hot tea is left in a cool room. It automatically cools off. This process satisfies the first law of thermodynamics, since the amount of heat energy lost by the tea is equal to the amount of heat energy gained by the surrounding air. The reverse process, that is, the hot tea getting even hotter in a cooler room as a result of heat transfer from the room, never takes place. This process is possible, but it does not violate the first law as long as the amount of energy lost by air is equal to the amount of heat of energy gained by tea. Next, let us consider a paddle wheel mechanism which is operated by the fall of a mass. The paddle wheel will rotate as the mass falls and steers a fluid within an insulated container. As a result, the potential energy of the mass decreases and the internal energy of the fluid increases in accordance with the conservation of energy principle. However, the reverse process, that is raising the mass by transferring the heat from the fluid to the paddle wheel, does not occur in nature, although doing work which does not violate the first law of thermodynamics. From these examples, processes proceed in a certain direction and not in the reverse direction. So here's a short summary of what the first law does and what it doesn't. And it seems that there must be some natural principle in addition to the first law of thermodynamics which governs the direction in which a process can take place. This principle is known as the second law of thermodynamics. A process cannot occur unless it satisfies both first and second law. Before we study the second law, let's discuss some thermal devices and their performance, which will help us understand thermodynamics better. The thermal reservoir. Now, a thermal reservoir is a large system from which a quantity of energy can be absorbed or added as heat without changing its temperature. The atmosphere and sea are examples of thermal reservoirs. And any physical body whose thermal energy capacity is large respective to the amount of energy it supplies or absorbs can be modeled as a thermal reservoir. A reservoir that supplies energy in the form of heat is called source, and the one that absorbs energy in the form of heat is called a sink. Heat engine. A heat engine is a cyclically operating device that absorbs energy as heat from a high temperature reservoir and converts part of the energy into work and rejects the rest of the energy as heat to a thermal reservoir at a lower temperature. The working fluid is a substance which absorbs energy as heat from a source and rejects energy as the heat to a sink. The performance of any engine is measured by the term of efficiency, and it is defined as the ratio of net output produced by an engine to the amount of heat supplied to the engine. It is expressed by W by Q1, where W is work done, Q1 is the heat supplied from the heat reservoir at T1 temperature, and we know that W is equal to Q1 minus Q2, where Q2 is the heat rejected from the engine to the sink at temperature T2. So substituting those, we get efficiency is equal to Q1 minus Q2 divided by Q1. Okay. And since we know that temperature gradient and heat gradient are equivalent, we can also write it as T1 minus T2 divided by T1. Right. So this is the equation for efficiency, we can calculate efficiency either through the amount of heat or if the temperatures are known. The thermal efficiency of the heat engine is always less than 1, and it is a measure of how efficiently a heat engine converts the heat into work. Next is refrigerator. Now, refrigerator is a device which is used to remove heat from a cold system. In other words, it is used to maintain the temperature of a body lower than the surrounding. Okay. ACs, coolers and freezers are all refrigerators in terms of thermodynamics. Now, efficiency of a refrigerator is expressed in terms of coefficient of performance, which is the ratio of heat extracted to the work input. COP of a refrigerator can be given as Q4 by W, where T3 and T4 are high and low temperatures of the reservoirs respectively. Note that the value of COP can be greater than unity. It is usually opposite of thermal efficiency, which can never be greater than 1. Next is heat pump. It is a device which is used to supply heat to a hot system. That is, we can say it is used to maintain the temperature of a body higher than the surroundings. For example, room heaters that we use during winter season. Again, the efficiency of heat pump is also given by COP, which is heat supplied divided by work input. And this is the formula for it. Now let's look at some of the MCQs based on the limitations of the first law of thermodynamics. Question 1. Which of the following is a limitation of the first law of thermodynamics? A. It cannot quantify energy. B. It does not distinguish between heat and work. C. It does not specify the direction of heat transfer. And D. It violates the conservation of mass. Now, the first law deals with energy balance but not with feasibility or direction. That is handled by the second law. So, the answer will be C. Question 2. A thermal reservoir is a system that A. cannot store energy, B. has variable temperature, C. supplies or absorbs finite heat without temperature change, D. has low heat capacity. The answer is C. Question 3. In a heat engine, which of the following is true? A. All heat absorbed is converted to work. B. No heat is rejected to the sink. C. It absorbs heat, converts some to work and rejects the rest. D. It operates without a temperature difference. We just learnt that heat engines must reject some heat to a sink. That is, 100% conversion of work is impossible. So, answer will be C. Question 4. The efficiency of heat engine is given by. Efficiency is the ratio of net work output to the heat input of the heat engine. Right. So, W net by Q in. Question 5. A refrigerator working between two thermal reservoirs transfers heat from a low temperature body to a high temperature body. What is required for this to happen? So, answer will be B, input of work, because work is required to transfer heat from a cold body to a hot body. To transfer heat against the natural direction. Question 6. The performance of a refrigerator is expressed using A. thermal efficiency, B. entropy generation, C. coefficient of performance, D. mechanical advantage. Answer is C. coefficient of performance. The COP of heat pump is defined as, answer is B, because for heat pump COP is the heat delivered to the hot surface per unit of work input. Question 8. Which of the following best represents the limitations of the first law then applies to heat engines? A. Heat engines can run forever without fuel. B. It does not account for the quality of energy. C. It cannot model ideal gases. D. It ignores changes in pressure. Now, first law allows for heat conservation, but it does not differentiate between usable and unusable forms of energy. So, answer will be B. And these are the interview questions you can get asked. So, we know why first law is not sufficient to describe heat systems. And we require the second law of thermodynamics, which we will study now. The second law of thermodynamics is a general principle which places constraints upon the direction of heat transfer and the attainable efficiencies of heat engines. In doing so, it goes beyond the limitations imposed by the first law of thermodynamics. The second law explains why energy transfers are not 100% sufficient. And it also states that entropy or disorder always increases in a closed system. There are two statements that we are going to study in the next slide. And the applications of second law are in heat engines, refrigeration systems, and power generation. Now, what is Kelvin-Planck statement? It says that it is impossible to devise a cyclically operating device which produces no other effect than the extraction of heat from a single thermal reservoir and delivers an equivalent amount of work. Heat engine with single thermal reservoir is not possible. Okay, for 1 ton engine, the thermal efficiency is equal to 1. But actually, no heat engine can have the efficiency equal to 1, right? The Clausius statement says that it is not possible for heat to flow from a colder body to a warmer body without any work having been done to accomplish this flow. Energy will not flow simultaneously from a low temperature object to a high temperature object. And this precludes a perfect refrigerator. The statements about refrigerators apply to air conditioners and heat pumps also, and they embody the same principles. So this is the second form or the Clausius statement of second law. We can simply say that it is impossible to construct a device that operates in a cycle and produces no other effect than the transfer of heat from a lower temperature body to a higher temperature body. There are many propositions that are derived from the second law, and this is the list of them. We have already discussed about the Clausius statement, and now we will discuss the rest of them in the next few minutes. Before that, what is a perpetual motion machine of the second kind, or PMM2? So the PMM2 is the machine which receives heat energy from hot reservoir and converts it into equivalent amount of work. That is, PMM2 gives 100% efficiency. Therefore, it is impossible to construct and it violates the second law of thermodynamics. If we look at it this way, PMM2 is the opposite of Kelvin-Planck statement. Now coming to Carnot theorem. The Carnot theorem states that no heat engine operating in a cyclic process between two fixed temperatures can be more efficient than a reversible engine which is operating between the same temperature limits. There are two corollaries of this theorem. First is, all reversible engines operating between the same temperature limits have the same efficiency. Second, the efficiency of all reversible engines depends only on the temperature limits of the reservoirs which is independent of the nature of working fluid. And all these three statements are also corollaries of the second law of thermodynamics. Now, coming to the absolute thermodynamic temperature scale. It is a temperature scale which is independent of the properties of the substances that are used to measure temperature. This temperature scale should be very much useful in thermodynamic calculations and its derivation using some reversible heat engines. Now, based on the corollaries of the second law of thermodynamics, all reversible heat engines have the same thermal efficiency when operating between the same two reservoirs, and the efficiency of the reversible heat engine is independent of the working fluid and its property. The reservoirs are differentiated by their temperature as a cold reservoir or a hot reservoir. Therefore, the efficiency of heat engines is a function of the reservoir temperatures only. You can see the derivation for your reference. Now, this temperature scale is known as the Kelvin scale, and the temperature measured on this scale will be the absolute temperature of any body. Now, let's move on to Clausius Inequality. Clausius Inequality states that when a system undergoes a cyclic process, the summation of dq by t around a closed cycle is less than or equal to 0. Now, let's consider an engine operating between two fixed temperature reservoirs T1 and T2. Let dq1 be the unit of heat supplied at temperature T1 and dq2 be the unit of heat that is rejected at temperature T2 in a cycle. Then the thermal efficiency will be dq1 minus dq2 divided by dq1. Right. The thermal efficiency of any reversible engine on the same temperature will be given by T1 minus T2 divided by T1. And since no engine can be more efficient than the reversible engine, the efficiency of the actual engine cycle must be less than the reversible cycle. Hence, we can derive that for the entire cycle, the closed integral of dq by t is less than or equal to 0. And this equation is known as the Clausius inequality, and it provides the criterion for the reversibility of a cycle. Now let's look at some MCQs based on this second law of thermodynamics. Question 1. The second law of thermodynamics asserts that A. Energy is always conserved. B. Work can be converted fully into heat. C. Heat cannot be fully converted into work without losses. And D. Mass can neither be created nor be destroyed. The answer is C. Because second law defines the direction of processes and limitations on energy conservation, unlike the first law. Question 2. A perpetual motion machine of the second kind violates A. zeroth law, B. first law, C. second law, D. law of conservation of mass. Answer is C. Question 3. Carnot's principle states that all reversible engines between the same two temperature reservoirs have equal efficiency. B. Real engines can be more efficient than reversible ones. C. Efficiency increases by lowering the source temperature. D. Heat engines can work in a single reservoir. Correct answer is A. Because Carnot's principle sets an ideal upper limit for efficiency and independent of the working substance. Clausius inequality is a mathematical expression of A. First law of thermodynamics, B. Entropy increased in reversible systems, C. Second law of thermodynamics, and D. Conservation of energy. So the answer is C. Second law of thermodynamics, because Clausius inequality, that is the equality of reversible and inequality for irreversible cycles. Next question. For a reversible cyclic process, Clausius inequality becomes A greater than 0, B less than 0, C equal to 0, and D undefined. So the answer will be equal to 0. So here are some interview questions that you can check out. Since this is too much to process, let's take a break. We will cover the rest of the sections in the next session.